it's time for us to get started. And this is our 15th lecture. And today is the snowfall that we're having. And I'm very grateful to see as many of you here. So we have 6 people here. That's pretty strong, considering how bad the weather is. The weather is bad enough that even though I left probably 45 minutes earlier than what I normally do, I was unable to get here for my first class. So I had to cancel a class today, which is very unusual for me. And but I didn't make it till about 9:15. Class started at 9. Really, the weather has no effect on what I'm about to say, but I didn't get your papers too graded. So I don't have them graded to hand back, and the weather didn't have anything to do with that. I'll grade them later today, and I might, I'll grade them later today, and then you'll get them back on Wednesday, okay? All right, the next thing I wanted to tell you is that I wanted to open up the floor to any questions that you have about homework 2, which you haven't got back yet, or homework 3, which you have gotten, but it's to be turned in, I think it's on Monday?
The 23rd.
Okay. If you have any questions about that, or anything that we've covered, that I'm wanting to entertain questions from you. Does anybody want to ask about anything at this point? Remember, homework 3, if you haven't gotten it, I've got, I think, extra copies. And in addition, homework 3 has 6 problems on it. The 6th problem is kind of situated to the right there after 5. Yes, sir, Corey?
For number 5 on homework 3, are we just going to kind of use the properties that we're going to finish proving today to show that they're the examples that were given are divergent sequences?
No. So in problem number 5, you're looking for examples of 2 divergent sequences such that if you subtract them, they converge, and we're not going to have them equal to each other, okay? But if you subtract them, they will converge, okay? But they're not the same as each other. And if you divide them, even though they're both divergent, it will converge, okay? And then problem 6 says, y is 4 to the n. My handwriting is so bad. Problem 6 says, y is 4 to the n as a sequence diverge. And I didn't give a point value for that, nor did I give a point value for 5b. 5b is worth 1 point. 6 is worth 1 point. It's a quick, you say one thing about that sequence, and it says, well, that's why it must diverge. Did I answer your question?
Yeah, I didn't read all the way through. I was thinking that both sequences had to diverge, and no matter which operation you did on them, they would still diverge.
No, if you take 2 divergent sequences, if you subtract them. Matter of fact, I had the stipulation that they can't be the same sequence, but if you take the sequence n, which diverges, why does n diverge? Why would you say the sequence is always in, 1, 2, 3, 4, 5? Why would you say it diverges? Say it again.
It's not bounded.
Yeah, that's a good reason for why a sequence might diverge, problem 6, is that it's not bounded, okay? And so if you take n, it's a sequence that doesn't converge because it's not bounded. And if you take maybe n again, it doesn't converge because it's not bounded. N minus n is 0, so it always converges, 0. It's a constant sequence. But I'm not allowing you to take the same sequences, okay, in problem 5a. But that's an example of 2 divergent sequences such that if you subtract them, you do get a convergent sequence. I want something different. Anybody else with anything? It's okay to ask. Well, I'm sorry that I don't have your homework graded. I'm sorry because it'd be nice for you to have it back. And number 2, I'm sorry because I still have it to grade. So I don't like that. I wish I would. I was done. But let's move on then. Here's what we were. So let's recall what we mentioned earlier. We're in the middle of the theorem. It says, suppose this is a theorem. we suppose that, all right, if x sub n converges to x, y sub n converges to y, then what we have were 4 parts. So I'm writing it a little different than what I had written before, Chuck. But the 4 parts are x sub n plus y sub n. It's going to converge to x plus y. We did that. The second thing we want to show is x sub n minus y sub n. It converges to x minus y. We will do that. And it's the same essentially the same proof as part 1. Part 3, that x sub n times y sub n converges to x times y. And part 4, if y sub n is different from 0 for all n, all the natural numbers, and y itself is different from 0, then we're going to show that x sub n over y sub n converges to x over y. So those are what we want to do. We're going to start with part 2 in just a second. Okay, so for part 2, so here, proofs, we're going to let x sub n be a convergent sequence say x sub n converges to x. So the limit as n goes to infinity of x sub n equals to x. We're going to do the similar thing for y sub n. We're going to let it be a sequence, this conversion. So we're going to say the limit as n goes to infinity of y sub n equals to y. So for part 2, we want to show the limit as n goes to infinity of x sub n minus y sub n. We want to show that that's equal to x minus y. That's what we are. That's what we want to show. Adam, these proofs all go the same way when we want to show a convergent sequence at this point of our careers. To show this x sub n minus y sub n converges to x minus y, we're going to start off the proof with a phrase. What is it? Remember? It's okay to say that.
E is greater than 0.
Let epsilon be greater than 0 be given. What do we need? How about it, Megan? That's right. We need a k, element of natural numbers.
Such that for all n is greater than or equal to k.
Right, Corey? What can you say? Absolute value of? Somebody tell me what to write.
Quantity of x minus y sub n minus quantity of x minus y would be less than epsilon.
That's right. That's what we want to show. That's correct. Okay. So let us know that that quantity that we're trying to look at, the absolute value of x sub n minus y sub n minus the quantity x minus y, that's inside absolute value. The same thing as rearranging the terms. X sub n minus x plus, here it will be y minus y sub n. That's the way I'll rewrite it. So I'll get that out of the way, let you look at it. That's the way of rewriting it. And what we can do is we can think of the first terms, x sub n minus x, as one thing. Plus, we can think of this next two combination of terms being as one thing. So here's what I'm thinking. I've got one thing plus another inside absolute values. And I know that's less, I'm trying to show it's less than epsilon, but I know that quantity is less than or equal to, using the triangle inequality, x sub n minus x plus y minus y sub n. But that's equal to x sub n minus x inside absolute value plus, this is minus 1 times y sub n minus y inside absolute values. And that's equal to x sub n minus x plus, this will be y sub n minus y. Hi, Brad. So we're in that second part of that theorem that we ended with last time. We want to show this quantity right here is less than epsilon. We know this quantity is less than the absolute value of x sub n minus x plus the absolute value of y sub n minus y. I now want to show that this addition is less than epsilon. To show this addition is less than epsilon, I'm going to show each part is less than epsilon over 2. That's what we did last time. That's right, Corey. And so what I'm thinking is, look, we want to show that x sub n minus y sub n is really close to x minus y after some point, okay, in the terms of the sequence. And the way we're going to show that this is small, less than epsilon, is by showing this is small and this is small. How do I know that x sub n minus x is small? Because x sub n converges to x. So I can make all the terms of x sub n be really close to x after some point in the sequence. Similarly, because y sub n converges to y, all the terms of y sub n after some point of that sequence gets really close to y. Is that okay? So here's what I'll write. Since the limit as n goes to infinity of x sub n equals to x, then there exists, I'll say, a case of one element of the natural numbers such that for all n bigger than or equal to case of 1, the absolute value of x sub n minus x, I can make this be smaller than whatever I want. What I want it to be smaller than, do you remember what it was? Right. Similarly, since the limit as n goes to infinity of y sub n equals to y, there exists a case of 2 element of the natural numbers such that for all n bigger than or equal to case of 2, we have the absolute value of y sub n minus y is less than epsilon over 2. So we have both of the things we want happening, but they may not be happening at the same point. So one's happening at case of 1, one's happening at case of 2. To make sure that they're both happening after some point on.
You do change the absolute value of case of 1 minus case of 2?
No, that's close, but not quite. We could do the addition of the absolute values of case of 1, case of 2, or just case of 1 plus case of 2. But that's not generally what we do. But you could do the addition of them. What do we generally do? Does anybody remember the trick? What we normally do?
K equals the max.
The maximum. That's what we normally do. So you want to push beyond the biggest one of those two numbers. So we're going to let K equal to the max of case of 1 and case of 2. Then, for all n bigger than or equal to k, we have the absolute value of x sub n minus x is less than epsilon over 2, and the absolute value of y sub n minus 1 is less than epsilon over 2. So summarizing, thus for all n bigger than or equal to k, the absolute value of x sub n minus y sub n minus the quantity x minus y, which is going to be, as we've shown before, is less than the absolute value of x sub n minus x plus the absolute value of y sub n minus y. We'd already shown that word, okay? Which is going to be less than This part right here is less than epsilon over 2 plus epsilon over 2, which equals to epsilon. So, for all n greater than or equal to k, the absolute value of the quantity x sub n minus y sub n minus x minus 1 is going to be less than epsilon. That means that the limit, as n goes to infinity, of x sub n minus y sub n equals to x minus 1. And that ends that part of the proof of the theorem. That was statement 2. Wait just a second. Does anybody have a question about what I've done? Kind of hard to have a question when it's coming at you so fast. It's just hard to even get it down. Let's give everybody a second.
So we had less than or equal to, then less than, then equal to,
Right.
and this.
So here's what happens.
Well, I'm sorry, I understand. It's just in my notes from last time I had less than or equal to and less than and less than. So did I write it down wrong?
Well, this part's equal to epsilon.
Right, okay.
So here, I'm just saying this part is equal to epsilon. Really, last time I should have said this same part is equal to epsilon, but overall we get that this quantity is less than epsilon. We get it less than because of this inequality right here. Once you get that step, you've got something smaller on the left. Anybody else with a question or comment? Okay. Well, the third part of this theorem was we want to show that the product, the limit of the product, equals to the product of the limits. So that's x times y. That's what we want to show here. And remember, we're assuming that x sub n converges to x and y sub n converges to y. How do I show this sequence converges to this number? Well, in our proof, it's always the standard format. What's the first thing we're going to say? Epsilon. That's right. So we're given some distance. We're calling it epsilon, greater than 0, be given. And what we're looking for is, as Megan told us last time, is we need a k. And what does k represent? It's a spot in the sequence. Such that from that spot on, the terms of the sequence from that spot on, their distance from x times y is less than this positive number that was given to me. Well, here's what I'm going to do. I'm going to say the thing that we want to make small, so x sub n, y sub n minus x times y. That's the thing we want to make small. Well, what I'm going to do is I'm going to add and subtract the same thing. So I'm going to rewrite what's inside absolute values as something that's it's the same thing as, but will involve two more terms. So I'm going to say x sub n, y sub n, and then I'm going to say minus, let's say x, y sub n, and then plus x, y sub n, minus x, y. So let me back away, and you can see that those two things are the same thing. In that, here's the two terms involved, here they still are involved, and what I've just done is added and subtracted the exact same thing. This is true no matter what n we're talking about. again, as we've done before, this combination of numbers, subtraction between two numbers, and these subtraction between two numbers can be thought of as one single number. So we think of this as one thing plus another thing inside absolute values. And using what we've been using quite often here to rewrite this as two absolute values. What fact? The triangle inequality. That's right, Corey. That's right, Audrey. We say this is less than or equal to the absolute value of x sub n, y sub n minus x, y sub n plus the absolute value of x, y sub n minus x, y. And then I'm going to say, well, this is the same thing as the absolute value of, I can pull out a y sub n, and I have x sub n minus x, plus here, I can factor out an x, and I have y sub n minus y. Get out of the way for a second. Let me write down one more line there. In that first absolute value, really we've got a product. Absolute value of a product. And one of the theorems that we learned about absolute values is the absolute value of one thing times another is the same thing as absolute value of the first times the absolute value of the second. Plus, same thing here, this would be the absolute value of x times the absolute value of y sub n minus y. And my goal is to make this quantity right here be less than epsilon. This is my goal, to be less than epsilon. What I've got is this quantity right here is less than this, less than or equal to this. So I want to make this whole thing be small. Well, here's what I know. Look, y sub n is converged to y. So I can make this be as small as I want. And y is some fixed number. It's what the y sub n is converged to. So it's a fixed number. I'm sorry, x is what's here. X is some fixed number. Okay? So I can make this be so small that when I multiply it by x, it's really a small number. Is that okay? I can make this be really small. Since x sub n converges to x, I can make this quantity right here, this absolute value of x sub n minus x, be really small. The only fear is, even though I can make this be really small, the only fear is, what if y sub n's are getting really big? That's right, Brad. Remember, I want this whole thing to be small. Is that okay with everybody? So I make this small. This is a number. It's already fixed. Small times whatever fixed number, that's going to be really small. You know, I just make this really, really, really small. This is really, really small. The only thing that's moving here, n changes. Well, for y sub n, the absolute value of it might be getting really big. But it's not. How do I know it's not getting really big? Because y sub n converges to y, that means that the absolute value of y sub n's, or the y sub n's as a sequence, if you give me a convergent sequence, which y sub n is, y sub n's, if they're convergent, then they are bounded. That's right. And so let me use that here in just a second. Let me get some space. And before I use that, let me remind you kind of what's the goal here. The goal is I want to make this whole thing be less than epsilon. So what I'm thinking is to make this part be less than epsilon over 2, and this part to be less than epsilon over 2. Okay, so that's what I'm thinking.
Let me just apply the first one that we are approved.
Well, we're going to use the definition. We don't have an addition between two convergent sequences here. Okay? We don't have an addition. That's the first thing. So no, but we can use the definition of convergence. But first, let us recall this. Since y sub n converges to y, then y sub n, as Corey told us, is a bounded sequence. Is that okay with everybody? It's a bounded sequence. Thus, what does it mean to be a bounded sequence? What's its definition? And look, I'm going to help you, okay? I'm going to say what the answer is. But this is why it's important to know those definitions. Now, I'm not saying, oh, you have to know them in this instance. But right now, I'm going to use one. So what does it mean for y sub n to be bounded? It means there exists some m that's positive, an m greater than 0, such that for all n, all natural numbers n, little n, the absolute value of y sub n is less than m. Is that okay? Thus, there exists an m greater than 0, such that for all n element of natural numbers, the absolute value of y sub n will be less than or equal to m. Therefore, remember this thing we wanted to make small, x sub n, y sub n minus x times y. That's the guy we want to make less than epsilon. What do I know it's less than or equal to? I know it's less than or equal to the absolute value of y sub n times x sub n minus x plus the absolute value of x times the absolute value of y sub n minus y. That's what I already had. That was that last line on the other board. What I'm going to do is get something bigger than this quantity, than the right-hand side. And I'm going to write down everything else as the same as what I've got, except I'm going to replace one of the items, only one of the 4 items, by something that's bigger than it. And it's from the previous line. The absolute value of y sub n is less than or equal to m. So where there's a y sub n here, I'm just going to replace it with m. And so I'm writing down something bigger. Okay, well, now, here's what I'm thinking. I want this quantity right here to be, overall, I want this quantity right here, Megan, to be less than
Over 2.
epsilon over 2, okay? I want this chunk to be less than epsilon over 2. So, Adam, I want this to be less than epsilon over 2. M is fixed, Corey. Okay? Melissa, M doesn't move. So, what does this guy have to be less than? Such that when I multiply it by m, I'm less than epsilon over 2. Well, shouldn't I replace this with epsilon over 2m? Remember, if this was epsilon positive over 2m, the m that's here in the bottom, and the m that's here would, and you just be left with epsilon over 2. Is that okay? So can I make the absolute value of x sub n minus x be less than epsilon over 2m for some group of n's? Well, the answer is yes, because the x sub n's converge to x. So here's what I'll say. Since the limit as n goes to infinity of x sub n equals x, then there exists a k-1 element of the natural numbers such that for all n bigger than or equal to k-1, the absolute value of x sub n minus x will be less than, so it's going to be epsilon over 2m. So there's a little bit of things to think about here, the 2m here. First of all, the reason that I can say this statement is because the x sub n's converge to x. And what I need to be writing over here is like a new epsilon. And the only quality on that distance is that it has to be greater than 0. Epsilon is greater than 0. You divide it by 2, you're still greater than 0. What kind of number is m? Greater than 0. So everything involved is greater than 0, so the whole division is going to be greater than 0. Is that okay? That's why we need to make sure that we're noting that m is greater than 0 here. Is that okay? That's something that's important. Okay, so I get that. Now, what do I need to make the y sub n's minus y be less than? Times, say it again, epsilon over 2, and in the bottom with 2 needs to be x. Okay, that's right. And let me tell you, I think that's what our book says, but there's a little bit of a problem here. I think we need to break this up into cases. So case 1. Audra said, hey, look, we're going to make this y sub n minus y be less than epsilon over 2 and then x in the bottom. But the problem with the absolute value of x in the bottom is We know the absolute value of x is greater than or equal to 0. But what if it's, can't be less than 0? What if it's equals 0? That's right. That's the problem. We'd be divided by 0. Is that okay? So case 1, if x equals to 0, okay, then what we have is the absolute value of x sub n, y sub n minus x times y is less than, here we have m times absolute value x sub n minus x, which is plus, and then we have 0, right? Plus 0. That's what we have, plus 0. So, for all n bigger than or equal to k sub 1, the absolute value of x sub n times y sub n minus x times y will be less than or equal to, or will be just less than, m times epsilon over 2 times m, which is equal to epsilon over 2, which is definitely less than epsilon. So in this case, the limit as n goes to infinity of x sub n times y sub n will be equal to x times y. What's the other case? If x is, I'm just going to have one case. Either x is 0 or it is not 0. Did I not turn this? I guess I didn't turn this. So here, what we did was the case is because of the dividing by absolute value of x. And what we said was if x is 0, then remember what we had was the absolute value of x plus a times the absolute value of y sub n minus y. But the absolute value of x in this case would just be 0. 0 times something is 0. So that's why I'm plugging in 0 here. And so here, as long as you're bigger than k sub 1, where x sub n is really close to x, then you get that the absolute value of x sub n times y sub n minus x times y is less than m right here. But I'm replacing the x sub n minus x by something smaller than it. That's epsilon over 2m, which produces epsilon over 2, which is less than epsilon. And so the spot in the sequence such that from that spot on we're very close to x times y is k sub 1. Okay? In this case. Sorry. Got excited. And case 2, as we said, is when x is different than 0. So in this case, the absolute value of x sub n, y sub n minus x times y, just rehashing, we know that this is less than or equal to m times the absolute value of x sub n minus x plus, here was the absolute value of x times y sub n minus y. Now I know that if I go bigger than k sub 1, n bigger than or equal to k sub 1, this guy is less than m, I'm sorry, this guy is less than epsilon over 2 times m. Okay? I want to make this guy be small. And I know this is not 0. And so what I'm going to do is since y sub n converges, I'll write it this way, limit n goes to infinity, y sub n equals to y. That means there exists a k sub 2 element of the natural numbers such that for all n bigger than or equal to k sub 2, the absolute value of y sub n minus y will be less than epsilon over 2 times the absolute value of x, which is going to be some positive number, and it is defined because x in this case is not 0. Now, look, I've got this nice spot where y sub n's behave like I want to. That nice spot is k sub 2. I've got this nice spot where the x sub n's minus x behave like I want to. That's called k sub 1. To make sure that both of the things that I want to have happen are happening, we have to push how far along into the sequence? The maximum. Same thing we've done before, okay? Thus, we're going to let, in this case, we're going to let k equal to the max of k sub 1 and k sub 2. Then, for all n bigger than or equal to k, we've got this x sub n times y sub n minus x times y is less than or equal to m times x sub n minus x plus absolute value of x times absolute value of y sub n minus y. But when your n is bigger than or equal to k, this guy is going to be less than m times epsilon over 2m plus, this is the absolute value of x, and this guy right here, y sub n minus y inside absolute values, is going to be less than epsilon over 2 times the absolute value of x. And then when you multiply this out, you get epsilon over 2 plus epsilon over 2, which equals to epsilon. I've got one less than here. So as a summary, so for all n bigger than or equal to k, we have that x sub n times y sub n minus x times y is less than epsilon. Thus, that says the limit as n goes to infinity of x sub n times y sub n equals to x times y. Part 4 has to do with the division. It's the hardest one. And I didn't look at it beforehand, so I'm a little nervous.
I have one question now.
Yes?
Right there, it's less than or equal to?
Yes.
Why just go to less than then?
Well, it's less than or equal to right here,
Yes.
but it's less than here because what I'm replacing the absolute value of,
Okay.
what I'm replacing the absolute value of x sub n minus x by is something that's bigger than it, strictly bigger than
Okay.
it. So x sub n minus x, we've erased this, but we established it a little bit earlier. When you're bigger than k sub 1 or bigger than k, this guy is less than epsilon over 2n. Likewise, here, this guy right here, which you can see still on the board, this guy right here is less than, not less than or,
Equal to.
it's just less than. Okay?
Makes sense though.
That's the reason we have less than. It can't be equal to anymore. That other part's a little bigger. All right. Well, let's get to that other part. It's more difficult. We've got about 10 minutes. So here, for part 4, we're going to let y sub n be different than 0 for all n element natural numbers, and we're going to suppose that y is different than 0. We want to show that the absolute value of x sub n, that the limit as n goes to infinity of x sub n over y sub n equals to x over y. That's what we want to show. Well, I told you I hadn't looked at this, and so I'm a little bit worried how it goes because I'm not as prepared as what I could be. But one thing that I am prepared to say is I know how this proof's going to start. We're going to say, let, that's right. What do we need? Well, that's right, we need a k. Element of the natural numbers, such that for all n bigger than or equal to k, the absolute value of x sub n over y sub n minus x over y will be less than epsilon. Okay. So we want Well, let me instead of we want. Let's start here. Note x sub n over y sub n minus x over y inside absolute values. Well, what am I doing here? I'm subtracting two fractions, Adam. How do you subtract two fractions? Got to get a common denominator. So this is the same thing as x sub n y minus x sub y sub n over y sub n times y. Now, that's the same thing. One of the things that we learned, and I'm not so sure this wouldn't be done as homework, problem, hadn't been done as homework, is the absolute value of the quantity, A over B, is equal to the absolute value of A over the absolute value of B. Is that okay? That's the same thing. So here's what I'm going to use. I'm going to use this fact. The absolute value of A over B is equal to the absolute value of A over the absolute value of B. That's a true fact. That's what I'm writing. You can do it in cases if you want, whether A is greater than or equal to 0, A is equal to 0, or A is less than 0. And in each case, you'd have a subcase about B. Okay? Subcase of B being greater than 0, B being equal to 0, or B being less than 0. But anyway, you can prove this, okay? If you hadn't already proved it. So that's a fact. So here I'm going to say this is the same thing as absolute value of x sub n y minus x y sub n over the absolute value of y sub n times y, which is the same thing as the absolute value of x sub n y minus x y sub n over the absolute value of y sub n times absolute value of y. Now here's what I'm thinking. Absolute value of y, I know that isn't 0, so everything's okay with that. And it's not going to change. It's a fixed number. The absolute value of y sub n's, they're moving. Now none of them are 0, but they're moving. Okay? They're changing based on it. Well, what I'm thinking is this is the same thing as absolute value of x sub n y, and then let's add and subtract. It's kind of the same thing. So let's subtract x sub n y sub n plus x sub n y sub n minus x y sub n. So I didn't change the top, I just changed the way it looks. So the absolute value of y sub n times absolute value of y. Again, what I did was I added and subtracted the same things. I didn't change it, just changed the way it looked. In the top, here's what I'm thinking. I'm thinking that this is one quantity. You subtract these two guys, you get a number. You subtract these two guys, you get a number. We got one number plus another number inside absolute values. By the triangle inequality, I know that's less than or equal to absolute value of the first part plus
Absolute value of the second part.
all right, so here's what I'm going to say. This is less than or equal to the absolute value of x sub n y minus x sub n y sub n. Okay, that's what I got. Plus the absolute value of x sub n y sub n minus x y sub n. Here, I'm going to make this over y sub n times y. Here, I'm going to have y sub n times y, just like that. So I broke it up into two fractions. So less than or equal to by the triangle inequality.
And we're going to want to factor out the x sub n in the first one and the y sub n in the second one.
That's right. And let's do that over here. That's right. Okay, so as Corey said, I can factor out x sub n in the first quantity. What I'm left with is y sub n. No, I'm left with y minus y sub n. And that's all over y sub n times absolute value of y. Plus, here we can factor out y sub n. And we've got x sub n minus x all over the absolute value of y sub n times absolute value of y. Here we've got a product, so absolute value of one thing times another. What can we do with that? We can rewrite that as the absolute value of absolute value of x of n times
Absolute value of y minus y.
all over the absolute value of y sub n times absolute value of y plus here the absolute value of y sub n times absolute value of x sub n minus x all over the absolute value of y sub n times absolute value of y. Look, just for convenience, I'll say this same thing is absolute value of x sub n times absolute value of y sub n minus y. That's just for convenience, okay? All of the absolute value of y sub n, absolute value of y, plus, here these two absolute values of y would,
Cancel.
and we're left with the absolute value of x sub n minus x over the absolute value of y. Now, you know, I've got what I originally wanted to be less than or equal to this quantity. So what I originally wanted was the absolute value of x sub n over y sub n minus x over y to be less than epsilon. That's what I wanted. So I'd like to make this whole thing be less than epsilon because it's the bigger of the things. Bigger of the two objects. So really I'd like for this to be less than epsilon over 2. And I'd like for this to be less than epsilon over 2. Well, this part's not so bad to get less than epsilon over 2. Okay? The reason is that the absolute value of y is fixed. It doesn't move. Okay? And the distance between x sub n and x, if I go far enough along in the sequence, I can make that to be really, really small. So I can make that quantity be really small. Is that okay? The quantity over here, I can make this guy be really, really small. Is that okay? This is fixed. So I've got something really small divided by a fixed number. I can make this part be really small. The absolute value of x, I need to make sure it doesn't get too big. And I need to make sure that y sub n doesn't get really, really, because it's in the bottom, get really, really small, Chuck said accurately. Is that okay?
So make it less than absolute value of y sub n times epsilon over 2 times epsilon.
Well, I can't let it depend on y sub n, okay? Because y sub n changes. It changes as n does. So I got to have a fixed quantity. First of all, I can put in something very easily for the fixed quantity here. Because I know, here it was, since, right, say it again?
You put an n.
Yes, and the reason I can do that is since the limit as n goes to infinity of x sub n equals x, meaning x sub n is convergent, then that sequence x sub n is, what's the right phrase? Anybody? Bounded. That's right, Corey.
No, not the very first. You had that less than or equal to there, right there, by your hand.
Yes,
Because of the
ma'am.
inequality.
Yes, ma'am.
Right, okay. I just wanted to make sure.
Yes, everything's less than or equal to right now. So there exists an m that's greater than 0 such that the absolute value of x sub n will be less than or equal to m, and that's true for all the unknown natural numbers. So the absolute value of x sub n over y sub n minus x over y, which we know to be less than or equal to that mess at the bottom of the board. The absolute value of x sub n times the absolute value of y sub n minus y over the absolute value of y sub n times the absolute value of y plus the absolute value of x sub n minus x over the absolute value of y. Okay, I can replace one part of it right here with something bigger than it, where it gets fixed instead of x sub n, where x sub n changes because it changes depending upon what n is. But m, which is always bigger than x sub n, that's absolute values and absolute values, is fixed. Okay, so this is going to be less than or equal to m times y sub n minus y over y sub n times the absolute value of y plus x sub n minus x over the absolute value of y.
What should be less than or equal to?
is less than or equal to, because this guy right here is less than or
Equal to.
okay. That's the reason we still keep the equality. All right, look, this guy can make really be small. Okay, y sub n minus I make that really be small. Okay, y is fixed, m is fixed. The problem over here is that y sub n is not fixed. It's moving. Is that okay with everybody? I don't want it to get really small, because if I divide by a really small number, the whole fraction gets really big. That's my problem. I don't want y sub n to be really small. This guy I can control because absolute value of y is fixed. I can make this be as small as I want. Well, I'm going to make it smaller than is epsilon over that. Epsilon times the absolute value of y over 2. That's what I'm going to make it smaller than. Epsilon times the absolute value of y over 2. That's what I'm going to use here. Okay? For this guy. But this part, I got some problems because of this. How do I know I can keep y sub n's away from 0, from getting really small? The reason I can is because y sub n converges to y, and y isn't 0. That's how come I can do it. Okay? But I got to do some work for that. And thank God we've run out of time. So that I'll show you that work next time. Thank you very much for your time and patience. Keep working on homework 3, and I'll give you back homework 2.